In the example of the DC motor, we'll revisit that again, and it's kind of a useful example, and we will use this as a motivation for building up lot of concepts around us. So the voltage or the input affects directly the current, but the current through the coupling between the state variables can affect the theta 2 dot, which is the angular velocity, and also the angular speed, and therefore through the voltage one should be able to control the speed of the motor. What about measurements? I measure theta 2, which is the speed or the angular speed, and if I see there is a nice, if I measure theta 2, there is a nice relation between theta. So here I have a nice relation between the theta and the current, and then the input voltage, and so on. So if I just measure the speed of the motor, I should also be able to determine the current by simply measuring the speed, right. In the first case, where we were controlling the speed, we called it as a controllable system. In the second case, now where we are measuring all the state variables by only measuring one out, where we are estimating all the other state variables with only one measurements, is called an observable system. Okay, why is this important? Look at now a system maybe of the form x1 dot is negative of x1, x2 dot is a negative of x2. Do not worry about inputs for now, and y is just x1. Okay. So, if I just say, can I just by measuring x1, can I get some information on x2? The answer is no, right. Whereas in the DC motor, just by measuring, so I had three states there, I had theta dot and the I. Just by measuring theta, I could get, just by measuring theta dot, I could know what was theta. Just by measuring theta, I could also know what was the current, just because of the inherent coupling between those two. Okay, why are we interested in this? We recall how our state feedback control law worked. State feedback control law was of the form u equal to minus kx. So, somebody has to give us the x for us to design the case. So, I had x dot is a system sitting inside here, x dot equal to ax plus bu. The x was fed through a minus k, and it gave me the control law u. So, somebody has to, so the x has to be fed back all the time. But what we see in case of a DC motor, that I can only measure theta dot. I do not have direct measurements of theta or the current, which means I cannot implement u equal to minus kx, because x is not for measurement. Only I have the only measurement is y. Not all states are measured, only some of those are measured. What do we do in this case? If I can construct, so from theta dot, if I am able to construct theta and I, then I can implement a controller of this form. In the DC motor, I could do the case. Here, the answer is I am not. Just by measuring x1, can I get some information on x2? The answer is no. And with that, we continue our discussions on lecture 2, which was on observability of the system. Okay. So, the duality we will speak a little later. what we the way we define observability is that a system AC is observable for any initial state, or if for any initial state there is a finite time such that x0 can be uniquely determined from ut and yt for 0 less than t, 0 t between 0 and tau. If the initial state xt naught, okay, so I mean I will just use xt naught and x0 interchangeably, they would mean the same without loss of any generality. If the initial state can be found from the measurements, okay, from measurements of the output and the knowledge of input over a finite interval of time, that if I can find what is x0 by ut and yt in some time, it could be 1 second, could be 1 hour, could be half a second and so on, the system is said to be observable. Otherwise, it is unobservable. So, observability refers to the ability of estimating a state variable. Okay. Now, this is a definition, and we are interested in, given x dot equal to ax plus bu, y equal to cx, is there a way I can look at a, b and c and say whether the system is observable or not? Okay, what does it mean again, right? We will try to do one more example before we ask ourselves how to check whether the system is observable or not. We will see another example. So, this system has two variables, the input comes from here, the output measured is x2, and it has another state here, right. So, there are two energy storing elements, so two states, okay, this can be x2, the voltage across, so be the same here also. Okay, so if u is 0 and x2 is 0, okay, we start with a condition where u is 0, x2 is 0 and x1 is some non-zero value, okay, but then still output is 0. So, any initial condition a comma 0 and u of t equal to 0 yield the same output. So, if x of 0 is 0 0, y is 0. If x is 1 0, y is 0. X is 2 0, y is 0. Okay. So, 3 measurements of the output does not give me any information of what could the initial state have been. Contrast this to the DC motor. If I give different speeds, say a larger speed could mean a larger value of current, intuitively speaking. So, I can make some distinguish, I can distinguish something with respect to what I observe as the output and what could be the speed. Here, there is no way to uniquely determine the initial state given the measurement y of t, which is x2, and therefore, the system is observable. Sorry, the system is not observable. Okay, so how do we go about doing this? I can start with a system of the form x dot is ax plus bu and y equal to cx. Okay, so we are interested in from y get x naught. Okay, so this solution I know. I substitute this into y equal to c times x and I get this large expression. What is unknown here? I can measure y of t, c is known, e power a t is known, again c is known, the input signal is known, everything is known. The unknown is x naught. Okay. So, we want to get x naught by just measuring y naught, and what we see here is this is a known quantity. Right. So, if I say y of t is c e a t x naught plus some known quantity. So, I know that this is y t whatever minus k known is c e a t x naught. Okay, I can just say subtract that quantity and say, well, this is my measurement, add it back and get what is my state. So, we can safely ignore these quantities, because these are known and the effect of this is known. So, I can add or subtract based on where I am. So, in our analysis, we will only focus therefore on a system of this form. Okay. So, now I will do some similar tricks. I will just use what I knew earlier for e power at. So, just use this definition, put it back here, and okay, this will expand to some terms which will now look like this. Okay. We again look at the definition. A system is said to be observable if for every state x t naught. So, can I determine x t naught? If t naught equal to 0, this will simply become x 0 by measurement of y t over a finite interval, right. This means that whenever a system is completely observable, right, or that when the system is completely observable, it means that every transition of the state affects every element of the output vector. Okay. So, a change in say the current will affect the speed, for example, right. Okay. Now, what is the math part is the following. So, based on this math, I just define these things and say, okay, I define the observability matrix, and the condition for observability translates to saying that the system is completely observable if and only if the rank of this matrix is n. Okay, similar conditions of what we see in controllability tests, that just give me A and C, I should be able to say whether the system is observable or not. Just similar to just give me A and B, I should be able to tell whether the system is controllable or not. Also, the key here is that everything depends only on the system properties A and B, not necessarily on what kind of input the system is subject to. It is independent of whatever is the input. Okay, let us understand the duality business through two systems S1 and S2, where x dot is Ax plus Bu, y equal to Cx. Here the controllability matrix would be B AB A n minus 1 B, and let us say the observability matrix which was of the form C CA n minus 1. I can write the transpose of it, the transpose of the observability matrix as C transpose, A transpose, C transpose, all the way till A transpose n minus 1 C transpose. So, system being controllable would mean rank of C is n, system being observable would mean the rank of this O or O prime. So, rank of a matrix is equal to the rank of its transpose, right. So, this will be the observability conditions. Similarly, I take another system Z dot is A transpose Z plus B, say some V, and say W equal to C, W equal to some B transpose Z. So, same system here, system is of the form A, B, C for the state input and the output, and here the second system is of the form with A replaced by A transpose, B replaced with C transpose, and C replaced with B transpose. Okay, so first let me look at what is the observability here. Observability would be these matrices B transpose A transpose power n minus 1. The observability transpose will have a good form B AB A n minus 1 B. Similarly, the controllability matrix here would be C A C A n minus 1 C. Okay. So, the rank for this should be n and the rank for this also should be n. Okay. So, when S1 is controllable, okay, when S1 is controllable, S2 is observable. Similarly, when S2 is, or when S1 is observable, then S2 is controllable. Okay. So, this is there is some kind of what is called as a duality now between controllability and the observability, and say S1 or S2 is the dual of S1 in such a way that if S1 is controllable, S2 is observable, S2 is observable, sorry, S1 is observable, S2 is controllable. So, this is what is meant here by the duality of controllability and observability. So, the pair AB is controllable if and only if the pair A transpose B transpose is observable. Similarly, with the observability of a pair, right. So, just relate this to controllability, observability, controllability of the S1 and S2. So, okay, why am I doing this, right? Suppose I want to look at observability properties of x dot equal to Ax, y equal to Cx, I can just translate this to controllability properties of say z dot equal to A transpose Z plus C transpose U. Both will mean the same. Okay, so what is, okay, some quick tests about given say A matrix, a C matrix, I compute the observability matrix, the rank is 2, the system is observable, we will see how the transfer function looks like. So, the transfer function will come to a second order system. I am just assuming that B is of the form 0, 1. Okay. So, this is for a observable system, the rank of the observability matrix is 2 and I see a good looking transfer function. Okay. In the second thing, so I take another example with a certain A, a certain C, a certain B. The rank of the observability matrix is 1, the system is unobservable. So, let us see, okay, what is happening here. I see some kind of a pole 0 cancellation that is happening, right. So, G of S, so I start with a system of n equal to 2, the transfer function has only one pole, indicating that a cancellation of S equal to 0. It's kind of similar system, right, 0, 1, 1, 2, C was 1, 0, now C became 0, 1, just see the subtle change. By measuring x1, I was able to see what was happening with x2, but I could not do the other way. Okay. So, the system becomes unobservable, and when the system is unobservable, we see a good pole 0 cancellation. Similarly, when the system was uncontrollable, we saw a pole 0 cancellation. Okay. And then to end, systems can be written in the observable canonical form. We will see why these derivations are useful while we do design for pole placement and so on. Okay. So, system of this structure, it is easy to verify observability for this way, that this kind of system with the zeros and ones of this form will always be observable. We will next see how do we exploit these properties for further analysis of systems.